Welcome to BrainOmega. Today, we're embarking on a hands-on journey to build a powerful time series prediction system using some of the most exciting tools in modern deep learning, transformers, and echo-state networks, ESN. If you've ever wondered how to tackle huge datasets, capture complex patterns over time, or experiment with state-of-the-art models, this video is your roadmap. We'll start with the big ideas, then gently dive into the actual code, showing you how each piece fits together. Whether you're new to machine learning or just curious about hybrid architectures, you'll find practical guidance and pro tips along the way. Let's first get our bearings. This project is organized into several Python files, each handling a key stage of the workflow. Main.py is our central command center. It downloads data, pre-processes it, initializes the model, and launches training. Dataset.py defines how we transform raw data into learnable sequences and prepare it for PyTorch's deep learning pipelines. Models.py contains the brains of our system, the hybrid transformer plus ESN architecture. Train.py handles the training and validation loop, including smart features like early stopping. Utils.py provides utility functions, such as our robust custom loss. And of course, we have a clear README to guide setup and usage. Let's explore these, step by step, and see how data flows through the pipeline. The full source code for this project is open to everyone and available on our GitHub. You'll find the link in the description of this video. I encourage you to explore the code, try it out yourself, and even contribute if you want. Having the source code will help you follow along with this tutorial step by step. One of the biggest challenges in time series analysis is structuring the data so that the model can learn patterns over time. In our dataset.py, we address this with two main components: a sequence creator and a PyTorch dataset class. First, we have a function called createSequences. Imagine you have a long stream of measurements, maybe network traffic data or sensor readings. This function slices that stream into overlapping windows, each of a fixed length, so the model can learn, given this recent history, what comes next. For every window, the target is simply the next value in the series. This is how we train our model to predict the future, step by step. Next, we wrap our sequences and targets in a custom class that inherits from PyTorch's dataset. This is a best practice, letting us easily batch, shuffle, and feed data to our model. When you call len on this dataset, you get the total number of training examples. When you fetch an item by index, you get both the input sequence and the target value as PyTorch tensors ready for the GPU. This modular design keeps things tidy and scalable, especially when datasets get huge. Now let's really dig into the core of our time series prediction engine, the hybrid transformer ESN model. This class brings together two world-class ideas: transformers, known for their ability to understand complex sequence relationships, and echo-state networks, ESNs, famous for their memory efficiency in time-dependent tasks. Let's break down the constructor step by step. Input projection. Our raw data, like a single feature per time step, is passed through a fully connected layer. This lifts the data into a higher dimensional space, D-model, giving the network more room to express relationships and patterns. Think of it like turning a single musical note into a rich chord. Transformer encoder. Next, we stack one or more transformer encoder layers, each with multiple attention heads. These layers let the model focus on important parts of the sequence, regardless of how far back in time they occurred. If you're new to transformers, attention means the model can weigh past events based on their actual relevance to the current prediction, not just how close they are. The dropout parameter helps regularize learning, fighting overfitting. Echo State Network, ESN. Reservoir. Now comes the fun part. We create a reservoir of neurons, a big block of nodes that mix and echo information as time passes. Input weights. Each new feature vector from the transformer is mixed into this reservoir using small, random, learnable weights. Reservoir weights. The reservoir is recurrent. At each time step, the previous state gets transformed by an internal connection matrix. We initialize these weights orthogonally for stability and scale them by a key parameter, the spectral radius. This is a core ESN trick. If the spectral radius is just right, usually less than 1, the reservoir will remember just enough of the past without becoming unstable or forgetful. Sparsity. To mimic how biological brains and real-world networks work, we zero out a large percentage of connections using a random mask. This reduces computation and makes the memory more selective. So, readout layer. Finally, the entire temporal history is distilled down to a single output using a linear layer. This is our prediction, usually the next value in the time series. The forward pass is where the hybrid power shows. Each sequence in the batch is projected and transformed. For each time step, the output of the transformer is fed into the ESN reservoir. The TAN activation is used here, a classic choice for keeping the reservoir's values nicely bounded and non-linear. The internal state is updated at every step, letting it echo the effects of past time steps forward, but always with a twist. The latest transformer-informed features influence every update. By the time we reach the end of the sequence, the reservoir state is a sophisticated blend of all the sequence information filtered by both attention and memory. The readout layer then maps this powerful high-dimensional state to our prediction. Why does this hybrid work so well? Transformers give flexible global pattern recognition, great for trends, periodicity, and sudden jumps. ESNs contribute fast, low overhead memory, tracking fine details and local interactions. Together, they allow the model to understand what to remember and how to remember it. For anyone tackling real-world time series, where trends, outliers, and subtle dependencies all matter, this design is both cutting-edge and practical. You can experiment with more layers, different spectral radii, or even change how the reservoir is updated to adapt this framework to your specific problem. Let's walk through the heart of our training process in train.py, focusing on the train and evaluate function. This is where your model learns and where all the magic of modern deep learning best practices comes together. We start by initializing two lists, train losses and test losses, which will store the average loss for each epoch. This makes it easy to plot learning curves and spot issues later on. We also set best test loss to infinity at first, so any real loss value will be better, and we use early stop counter to track if our model stops improving. Now for the main training loop. For each epoch, we switch our model to training mode using model.train. This is crucial in PyTorch. It enables features like dropout and batch normalization, which are only meant to be active during training. We set the epoch's training loss accumulator to 0. Next, we loop over all the mini batches from our train loader. Each batch contains a chunk of input sequences, X batch, and the corresponding targets, Y batch. We make sure both are on the correct device, CPU or GPU. Notice the unsqueezed left parenthesis negative, one right parenthesis. This adds an extra dimension to our input, matching what the model expects. For example, left bracket batch, sequence, one right bracket. Before each step, we zero out the gradients with optimizer.zeroGrad. This is vital because by default, PyTorch accumulates gradients. Forgetting to reset them would mix up updates from multiple batches. We run our batch through the model to get predictions, outputs, compute the loss against the ground truth, and call loss backward to compute gradients. The optimizer step method then updates all learnable parameters based on these gradients. The total loss for the epoch is updated by adding the loss for this batch. Once all batches are processed, we average the loss by dividing by the number of batches and append it to our list of training losses. After training, it's time to evaluate. We switch the model to evaluation mode with model.eval. This tells PyTorch to disable dropout and use running stats for batch norm, so results are consistent and not random. We use torch.nograd context to save memory and computation, since we won't be updating the model here. Inside this block, we repeat the batch loop for the test data, moving each batch to the right device, getting predictions, and summing up the loss. Again, we average the total loss at the end and store it. We also step the learning rate scheduler based on the test loss. This can automatically reduce the learning rate if improvements plateau, a trick that helps the model escape local minima. For transparency, we print out the training and test loss for each epoch so you can watch progress in real time. Now comes early stopping, which is a huge help when working with big data. If the current test loss is lower than our best ever, we reset the early stop counter and remember this as our best model so far. If it isn't better, we increment the counter. If the model hasn't improved for a set number of epochs, patience, we print a message and break out of training early. This saves time, resources, and usually gives you the best generalizing model. Finally, the function returns lists of train and test losses, which you can use for plotting or further analysis. When it comes to deep learning, the loss function you choose can make a huge difference, especially for regression problems like time series forecasting. Here in utils.py, we use a clever alternative to the classic mean-squared error, the log-cosh loss. Let's break down the code line by line. First, we calculate the prediction error for each data point. This is just the difference between what the model predicts, y-pred, and what the actual value should be, y-true. In PyTorch, this works element-wise, so you get an error for every single prediction. Next, we apply two mathematical functions, the hyperbolic cosine, cosh, and the natural logarithm, log. The hyperbolic cosine grows almost exponentially for large positive or negative numbers, but for small values, it's very close to 1. When you take the log of the cosh, you get a function that looks a lot like a squared error near 0, so it still punishes small mistakes, but grows much slower for big errors. This means the loss is less sensitive to outliers. Occasional wild data points won't totally dominate your model's learning process, which is a common headache with mean-squared error, especially in real-world data. Finally, we take the mean of all these losses to return a single scalar value. PyTorch's tensor operations make all of this run fast and efficiently on your GPU. This approach is particularly handy when your dataset isn't perfectly clean. Maybe there are measurement errors, occasional transmission spikes, or rare but huge anomalies. With log-cosh loss, your model can learn the general trend without getting distracted by those occasional big mistakes. You can easily swap in any custom loss function in PyTorch, just like this one. Try experimenting with different loss functions on your data. You might be surprised how much it can improve stability and generalization. With our data pipeline in place, main.py takes the role of conductor, orchestrating every stage from raw data to trained model. What's really special about this script is how configurable and reproducible it is, just like you'd want in serious research or industry work. First up, automatic dataset download. No more worrying about manual downloads or mismatched file paths. The Kaggle Hub library grabs the right dataset for you, meaning you can switch to new data sources with a single argument. Fantastic for benchmarking or exploring new domains. Next, we load and pre-process our data. We use pandas to read the dataset and focus on the length column, which is a typical feature for time series like traffic, network load, or signals. Limiting the number of samples, max data, keeps things memory efficient. We scale everything to 0,1 using min-max scaler. This step is crucial. Deep learning models are much more stable when features are normalized, letting the optimizer update weights smoothly and avoid numerical blowups. Then, we prepare sequences for supervised learning. Using our own create sequences function, we turn a long-time series into overlapping input-output pairs. Each input is a chunk of history. Each target is the value that follows. We split the data into training and testing sets. Always set a random seed, random state for reproducibility. Next, we wrap the arrays into custom PyTorch dataset classes and use data loader for efficient batching and optional shuffling. Now we initialize our hybrid model and get the device right. The script automatically uses your GPU if available, a huge speed up for big experiments. The model is parameterized from the command line, so you can tweak everything: hidden sizes, number of layers, reservoir memory, attention heads, just by changing arguments. This makes testing new ideas or tuning hyperparameters fast and consistent. For optimization, we choose AdamW, which is robust to noisy gradients and helps prevent overfitting with weight decay. Our learning rate scheduler is set to monitor test loss. If progress stalls, it automatically shrinks the learning rate, often helping the model escape flat spots and find a better solution. The actual training and evaluation happens with a single function call, passing in all the tools and parameters. All losses, metrics, and checkpoints are handled inside, making the script both clean and powerful. Finally, the argument parser gives you complete control from the command line. This is a best practice for any serious machine learning project. You never have to touch the code to run new experiments, just adjust the flags. It's easy to log, easy to repeat, and perfect for running on servers or in collaborative teams. This pattern, modular, command line driven, and device aware, is how professional ML pipelines are structured in both research and production. It's designed for speed, reliability, and extensibility, so you can push your ideas further, faster. And there you have it, a complete modern pipeline for time series forecasting designed for large-scale datasets and rapid experimentation. Each file plays a crucial role, from data preparation to model definition and training. The modular, configurable design means you can easily extend or adapt the system, try different datasets, play with the model's hyperparameters, or swap in new architectures. As a final tip, always start with a clear structure like this. Break your project into logical parts. Keep your code modular and use command line arguments to make experimentation painless. This not only makes your research reproducible, but also lets you scale up to bigger and more complex challenges. Thanks for following along on BrainOmega. If you enjoyed this deep dive, please like, subscribe, and leave your questions or ideas in the comments. What should we build next? Happy coding!